Namaskar. Now I'll continue my previous lecture. In three lectures, from last three lectures we are discussing about canonical transformation. In this lecture, we'll see that what are finally the conditions for a transformation to be canonical. In one lecture, I told you that if the Hamilton structure is preserved, Hamilton's equations of motion are preserved for the new coordinate system, then you say that your transformation equations are canonical. Then I told you that if Maxwell relations are satisfied, or if you can find a generating function, or if your expression, a particular type of expression is exact, then you say that your transformation equations are canonical. Now I'll discuss a third type of condition, and then we'll try to use these three conditions in one example to know the implementation of the three ways to find the transformation canonicality of the transformation equations. So I told you that there is one way that if you are with coordinates qi, pi and ti, you transform these two capital Qi, Pi and T with the help of transformation equations Qi, Pi and time, and Pi as a function of Qi, Pi and time. Then if for this system, for the old system, H is transformed to K, then if you can preserve the Hamilton's equations of motion, that is if delta Qi, delta Pi is Qi, delta Pi, sorry, K. Your K is a function of capital Qi, Pi and time. So if you can find delta K, delta Pi is equal to Qi, and delta K, delta Qi is equal to minus of Pi, if this is preserved. This is Qi dot, this is Pi dot. If these equations are, if this type of structure, which is true for Hamilton's equations of motion, is preserved for new system also corresponding to new Hamilton K, then you say that transformation equations are canonical. These are the transformation equations. So if 2 is satisfied, transformation equations are canonical. Right? Similarly, with the help of Hamilton's principle, we proved that if sigma of, this is one way, and the second way is if sigma of Pi dqi minus sigma of Pi d capital Qi plus k minus h dt is exact, then transformation equations are canonical. Equations are canonical. And if k is equal to h, that means t is not involved, then you are left with this condition only, that this should be exact. And from the exactness of this equation, this expression, we found f1. With the help of f1 we found f2, f3 and f4, and ultimately the Maxwell equations or some relations. So either we show that this is exact, or we show any of those relations to be satisfied, we may say that transformation equations are canonical. Now I come to the third way, third method. There are in fact 4 methods. One method will be discussed in the last unit, and the third method is that which is called the condition of bilinearity. That means the invariance of bilinear relation. Invariance of bilinear relation. If it is true, what is this relation? That if sigma delta pi dqi minus sigma delta qi dpi, this is an expression in old coordinates, is the same for the new coordinates, that means for capital Pi and capital Qi, if it is true, then we say that transformation equations are canonical. How we find this relation? You know that our old coordinate system is Qi, Pi in time. It is transformed to Qi, Pi in capital Qi, Pi in time. And for this we have Hamiltonian H, and for this we have Hamiltonian, say, K, right? So corresponding to the old system, the equations of motion are delta H delta Pi is equal to Qi dot, and delta H delta Qi is minus of Pi dot. These are the equations of motion. Now if I talk about this system, new system for new coordinates, so this is 5. For new coordinates, equations of motion are delta K delta capital Pi Qi dot delta K delta capital of Qi is minus Pi dot. These are the relations. Now I consider sigma, this one, this relation, delta Pi dqi delta Qi dpi. I am taking the one side of the relation. In this relation, if I pick old one, because this expression is in terms of old coordinates, then this is equal to sigma delta Pi. You see, this implies delta H delta Pi dt is dqi. Similarly, this implies delta H delta Qi dt is minus dpi. So I'll use these relations in this expression. So dqi may be replaced by delta H delta Pi dt and minus delta Qi. Now this dpi is replaced by minus delta H delta Qi dt, or write it in after certain changes in the places of the terms, plus summation delta H delta Qi dt. What is this? This is the variation of H with respect to delta, because variation of H is a function of small p. So variation of H, derivative of h with respect to q, delta qi, derivation of h with respect to p, and then delta pi. So as a whole, this is delta h and this dt. So this is one side. Similarly, if I use this one, I get delta k, delta pi dt is minus dqi. If I use this one, then I get delta k, delta qi dt is minus dpi. So for this side of 4, right hand side of 4, I'll use 9, relation 9. What is this side? Sigma delta pi dqi minus sigma delta qi dpi, right hand side. It is summation delta pi. Now what is dqi? Look at here, dqi is delta k delta pi dt with minus symbol. It is delta k delta pi dt. Come to this summation delta qi. Its value is delta k delta qi dt. Yes. There is certain mistake. This is positive. So this is positive and this is negative. So it is summation delta k delta pi summation delta k delta qi and dt. This is delta k. This whole is delta k dt. Now if your equations are not involving time, k is equal to h. So this is delta h dt. From 8 and 9, from 8 and 10, 8 and 10 implies that summation delta pi dqi summation delta qi dpi is the same for the capital letters, that means for the new coordinates. This is called the invariance of bilinear condition. So if this condition is satisfied, invariance of bilinear form, if this condition is satisfied, then again we say that the transformation is canonical. So this is the third way of proving your transformation to be canonical. Now we come to an example with the help of which we'll try to operate the three methods, right? So come to an example. Suppose I write, this is the third way. Suppose I am given q is equal to root 2p sine q and p is equal to square root of twice p cos q. Then I have to show that transformation equations are canonical. First of all, you look at the expression. This expression is, in this expression, q is a function of capital Q, capital P. In this expression, capital P, this is capital Q, is a function of capital Q, capital P, right? Now, because I have to use the three methods, so I'll go one by one. In first method, यानी कि I have to show that P dq minus capital P dq is exact. I'll try to show it. Here, what is dq? You can get its value. dq means derivative of q. So dq will be, first you differentiate with respect to p, 1 upon root 2p sine q dp, and then root twice p cos q dq. And what is dp? dp implies 1 upon dp implies 1 upon root 2p cos q dp 1 upon root 2p cos q dp plus minus square root of 2p sine q dq, right? But in fact, we do not require the 2. We require just the 1. Because in this expression, we need d of small q. So my work will be over here. P dq minus capital P dq will be, in place of small p, I may write root 2p cos q, and in place of dq, I may write 1 upon root 2p sine q dp plus root 2p cos q dq, right? And this is minus p dq. It is on our choice. Either we substitute in first term and put the second term as such, or we put in second term and put the first term as such. Suppose I am putting in the second term. Then in that case, I have to change these equations in such a way that I get capital P in terms of small q and p. I get capital Q in terms of small p and q, and then only I can do that. So I have chosen this part, and for this part I need dq, so I have found the dq from here. So in fact this dp is not required. This dp is not required. Now there is just the adjustment of the terms in this expression. I write this cos q sine q dp, because root 2p will be cancelled with this root 2p. So I'll get sine theta cos theta. So I am writing sine 2 theta upon 2 dp, and then combine it with this term. This will be twice p cos square theta and then minus p and whole with dq. It is sine 2 theta upon 2 dp plus I may take p outside. So it is twice cos square theta minus 1. Twice cos square theta minus 1 means cos 2 theta. Cos 2 theta dq. Now you can make it to be the perfect derivative of, exact derivative of p by 2 of sine theta. sine theta. If you differentiate p, you will get dp 1 by 2 sine theta as such, sine 2 theta, sorry, it is sine 2 theta, 2 theta. And if you differentiate sine 2 theta, you will get p as such, and this will be cos 2 theta by 2. So you are getting twice cos 2 theta. 2 will be cancelled with 2 and you will get this term. So you can get a function. This implies there exists a f. What is this f? P by 2 sine 2 theta. Therefore, this expression is exact. This expression is exact. So transformation is canonical. So this is one way of proving transformation equations to be canonical. There is another way to show that equations are canonical, which is the condition of bilinear, invariance of bilinear condition. That is, if sigma delta pi dqi minus sigma delta qi dpi is summation delta capital Pi d capital Qi minus summation delta capital Qi d of capital Pi. If this type of relation exists, then we say that the transformation equations are canonical. So in this also we may pick either this one or this one, because in your question you are having small q and small p in terms of these relations. You may also find the reverse relations. That means you can solve these two equations and then you can find capital Q and capital P in terms of small capital Q, capital P. That is new in terms of old. So if I solve those given equations, these equations, if I solve these equations 1, these two equations, I may get one also provide you that capital P is equal to half of P square plus Q square. You can very well solve these and find capital P and capital Q in terms of small variables, variables in terms of small letters, यानी कि old variables. Now I have to prove this condition to be satisfied. This is the one way. First way है ये. Now for the second way, this you can say 3. This is 4 and these are 5. From here you can find delta Q and delta P. Delta P is equal to, this will be the variation, delta P is equal to half of twice P delta P plus twice Q delta Q. This is the value of delta P. Now dP will be half of twice P dP plus twice Q dQ. Right? Now find delta capital Q. Delta capital Q is, because it is in tan inverse, 1 upon 1 plus Q square upon P square, and then 1 upon P delta Q minus Q upon P square. This will be delta, not D. Delta P. And solving this delta Q, you will get minus Q upon Q square plus P square delta P and plus P upon P square plus Q square delta Q. I think this will be 1 upon this one and then derivative of this, so 1 upon Q delta Q, right. I can find dq as well. I'm doing some mistake. This is P square of P and this is P square. No, so similarly dq will be minus Q upon Q square plus P square dP plus P upon P square plus Q square dQ. Now what I have to do, I will put in the right hand side of 4 all these expressions and I'll get the same expression as put on the left hand side. So it is simple calculation, you can do yourself. You put all these values in this side. I can do either way, another way, that I may consider these equations. I find the derivatives of small q and small p, and then putting those derivatives here, I can find the right hand side. So this is the second way to prove that your transformation equations are canonical. Now the third way is, we show that the Hamilton's equations are preserved. That means the Hamilton's equations are true for the new Hamiltonian. So in third way, I have to show that if your h is a function of q, p and t, if this is your function and k is the new Hamilton, k is a function of capital Q, capital P and T, then we have to show that delta k, delta p is equal to q dot and delta k, delta q is equal to p dot. That this type of preservation is there. If I can show that these relations are preserved, then it's okay. Then it simply means that your transformation equations are canonical. So for this, what we will do, we'll show that because I have to find expression in k and k is involved in h, right? So I know that if t is not involved, in your generating function or in your transformation equations, then k is equal to h, and I have to go to this k. I have to find the equations in terms of this k. So what I'll do, I'll find delta h, delta p and delta h, delta q. Why? Because I know that delta h, delta p is equal to q dot and delta h, delta q is equal to minus of p dot, right? What is this q dot? Q dot may be written as d q dt. This may be written as minus dp dt. And I know that there exists relations for q as a function of capital Q, p and time, and small p as a function of capital Q, p and time, and vice versa. It simply means that because I have to go from h to k and then small coordinates to old coordinates to new coordinates, so I may write this dq dt as delta q dq dt, and then delta q delta p dp dt. I may write in this way, right? Similarly, this will give minus delta p delta q dq dt and delta P, delta capital P, dP dt, right? It simply means that you need Q to be differentiated with respect to capital Q, so you will use this equation. You need Q with respect to P, again you will need this equation. So you should have an expression like this. And yes, we have an expression like this. These are the expressions of Q and P, old coordinates in terms of new coordinates. Similarly, if I come to this one, then I need to differentiate small p with respect to capital Q. So I need a relation between small p as a function of capital Q and capital P. Here you have to differentiate small p with respect to capital P. So again you need the same relation between small p, any old coordinates, and the new coordinates. So you can very well calculate all these. Now what about this delta H delta P? From k is equal to H, this delta H delta P is in fact delta H delta P is equal to, you may write it as delta H delta P is equal to, because H is K, so delta K, and K is a function of Q, and delta Q delta P. Similarly, delta K is a function of capital P, and then delta P delta P. This is your delta H delta P, right? So in third way, first of all, you want to find these relations. And this is 12. Or you may take delta H delta Q as well, because it has delta H delta Q. It will be delta K delta Q delta Q delta Q, delta K delta P delta P delta Q. So if I put these relations in these sides, I may pick any of the relation, either 10 or 11, and from these relation I'll find these equations. Suppose I am using 10. Equation 10 implies delta H delta P, delta K delta Q delta Q delta P plus delta K delta capital P delta P on left hand side, and on right hand side I have delta Q dq dt. dq dt means Q dot, so you write Q dot plus delta K delta P, and this is P dot. Now what is last to do? Just put its value, put its value, and put its value. You put the 4 values with the help of 4 equations. You can find delta Q delta P, you can find delta P delta P, because you have 4 relations. These are the 2 relations. Similarly, these are the 2 relations. From these 4 relations, you just find the values of these terms, these expressions, and then comparing the 2 sides, you will get delta K delta Q will be minus P dot, and delta K delta P will be Q dot. You can very well do it. You just put the values and compare. You will get these relations and say that Hamilton's equations are preserved, and therefore the transformation is canonical. So these are the 3 ways. Now you find questions on this and then try to apply the 3 conditions. You try to find out the generating function with the help of equations. You try to find whether the given equations are canonical or not, and you try to solve your dynamical system. So this is all about canonical transformation. Thank you.